Okay, algebra time. So remember, we have exam next Monday, 9 o'clock. And so let's just record this. And I said we'd have an optional review session Friday morning, 2 days. Which is, I guess it's the 14th. No, not the 14th. It's the 7th. And what the exam covers is group theory. And in particular, homework 7, 8, and 9. 9 is the latest one, which are kind of review for the exam. And I am happy to, I'm going to go over homework problems today, but I'm happy to start with any questions or problems you would like me to answer first. Any suggestions, questions, problems, whatever?
Well, Professor, what time on Friday would this review session be? Same time as class?
Yes, 9 o'clock.
Okay, thank you.
Okay, well, all the problems are interesting. Let me start with some in homework 9, because they're the newest. Number 1. So we have a function f from the real numbers to the complex numbers, defined by f of a number t is cosine 2 pi t plus I sine of 2 pi t. So t is a real number, and this is a complex number. This is the real part. This is the imaginary part. So for example, f of 0 is cosine of 2 pi times 0 plus I times the sine of 2 pi times 0. So that's cosine 0 plus I sine 0. And cosine 0 is 1 and sine 0 is 0. So this is just 1. F of a half is the cosine of 2 pi times a half plus I times the sine of 2 pi times a half. That is cosine pi plus I sine pi. Cosine pi is minus 1, sine pi is 0, so this is minus 1. F of 3/4 is the cosine of 2 pi times 3/4 plus I times the sine of 2 pi times 3/4. Right? This is, all we're doing is just evaluating the function. Right? This is cosine of 3 pi over 2 plus I times the sine of 3 pi over 2. So everyone learned pre-calculus. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is minus 1. So this is minus I. Right? So if you have a function, you need to know, first of all, how to calculate it, and if possible, and at least for simple values. And This is the function. Right? Any questions
Professor,
about this?
could you repeat the F0, 1/2, and 3/4? I can't see them really well.
F of 0?
Yes.
Well, this is the function. F of t is cosine 2 pi t plus I sine of 2 pi t. So when t is equal to 0, this is 2 pi 0, which is 0. And this is 2 pi times 0, which is 0. So this is just cosine of 0 plus I times the sine of 0. And you know the cosine of 0 is 1 and the sine of 0 is 0. So you get 1 plus 0 times I, which is 1. Any other questions? This is just, looking at the function and understanding what the function means. And we have to show it's a homomorphism. So we have to prove that the function f of t equal cosine 2 pi t plus I sine of 2 pi t is a homomorphism of groups. Right? F is a homomorphism from, so what are the groups? It's a function from R to the complex numbers. And in fact, this is always a non-zero complex number. So I can just write a little star there. So this is an additive group. And this is a multiplicative group. So we must show that f of two numbers, let's say s plus t, or I'll write x and y, doesn't matter. F of x plus y is f of x times f of y. That's what it means to be a homomorphism. So what is f of x plus y? That's the cosine of 2 pi times x plus y plus I times the sine of 2 pi times x plus y. Right? Just plugging in t equal x plus y. And then you know, or you're supposed to know, certainly, of course it came up many times, certainly came up in calculus, the addition formula for the cosine and the sine. So this is the cosine of 2 pi x cosine of 2 pi y. That's the addition formula for the sine, plus cosine of 2 pi x 2 pi y minus the sine of 2 pi x times the sine of 2 pi y. Right? If you just expand this using the addition formula for the cosine, it's the cosine of 2 pi x times the cosine of 2 pi y minus the sine of 2 pi x times the sine of 2 pi y, plus I times the sine of 2 pi x plus 2 pi y. So by the addition formula for the sine, this is the sine of 2 pi x cosine 2 pi y plus the cosine of 2 pi x sine of 2 pi y. Right? That's just the addition formula for the sine. So that's what f of x plus y is. Now, just separately, let's compute f of x times f of y, because I want to show these two are equal. So f of x, that's cosine 2 pi x plus I sine of 2 pi y times the cosine of, this is an x, plus the cosine of 2 pi y plus I times the sine of 2 pi y. So we're just multiplying two complex numbers. So you get cosine 2 pi x cosine 2 pi y minus the sine of 2 pi x sine of 2 pi y. And then you have plus I times sine of 2 pi x cosine 2 pi y plus cosine of 2 pi x. This is I, this times this, that's part of the imaginary part. Sine of 2 pi y. And if you compare this and this, they're exactly the same. So that means that f of x plus y is f of x times f of y. So, yeah. So we have a group homomorphism. It's a homomorphism from the additive group of real numbers to the multiplicative group of non-zero complex numbers. Okay. Any questions about this? This is just a little calculation.
Hello, Professor.
Yeah,
Question. So for more information about this, what chapter should we look at, or what topic?
it's group theory.
No, I mean, but like the actual subtopic or what this is called.
Group theory. This is the beginning of group theory.
Oh, it's the beginning. Okay.
So in the notes that I posted, it's all there. And if you look at the book by Clark, this is the beginning of chapter 2.
Chapter 2. Gotcha. Okay.
Group theory. Definition, examples, subgroups, cosets, quotient groups. Just the first 4 sections of that. I mean, it's really in the book by Alan Clark, it's all in very few pages. It's just from page 17 up to 39, 20 pages. Yeah. Oh, and then group homomorphisms, that's also in that chapter. It's a few pages later on. All right, that's all, just a little bit of group theory. That's all we've done. So we still haven't finished the problem. There's more to do. So we have R, the additive group of real numbers. C star, which is the multiplicative group. Of complex numbers. And this function from the additive group of reals to the multiplicative group of complexes defined by f for any real number t is cosine 2 pi t plus I sine of 2 pi t. And we just proved this is a homomorphism. So what is the kernel? The kernel of f, this is the definition, it's all real numbers t that get mapped to the identity. What is the identity when you're multiplying complex numbers? It's just 1. It's all real numbers t where f of t is 1. That is, it's all numbers t, real numbers, such that cosine 2 pi t plus I sine 2 pi t is 1. That means the cosine of 2 pi t is 1 and the sine of 2 pi t is 0. So this is all real numbers t where the cosine of 2 pi t equals 1 and the sine of 2 pi t is 0. So what are the numbers where the cosine is 1? So let's just recall. Cosine of x is 1 if and only if x is some integer multiple of n. X is 2 pi n for some integer n, right? I mean, that's what, just remember the graph of the cosine, right? 0, 2 pi, 4 pi, all the integer multiples of 2 pi. And sine y equals 0 if and only if y is pi over 2 plus some multiple of pi, right? Sorry, if sine of y is 0, what does the sine look like? It's equal to 0 if y is equal to some multiple of pi. So f of t is 0 if and only if 2 pi t is 2 pi n for some n integer. That's the kernel. So we have f of t is cosine of 2 pi t plus I times the sine of 2 pi t. For an integer n, f of n is cosine 2 pi n plus I sine of 2 pi n. That's equal to 1 plus I times 0, or 1. And that's the only time that f of t is equal to 1. So the kernel of the function f is just the integers. Okay, any questions about this? This is really a very important example. What about the image of f? So this is all complex numbers z such that z equals f of t for some real number t. So it's the set of all complex numbers cosine 2 pi t plus I sine of 2 pi t. What can we say about this? So suppose you take the complex number cosine 2 pi t plus I sine of 2 pi t. So if you have a complex number x plus yi, the length, or the absolute value, is the square root of x squared plus y squared, right? That's just, here you have the point xy in the plane. That's your complex number. And the length, just the Pythagorean theorem, that's z. This length of z is just square root of x squared plus y squared. It's just the length of the hypotenuse. So the absolute value of z is the square root of cosine squared of 2 pi t plus sine squared of 2 pi t. And cosine plus sine squared is 1. So the absolute value of z is 1. What do you call the set of points in the plane whose absolute value is 1? It's called a circle of radius 1. This is 1 minus 1. This point is a complex number, is I and minus I. This is the unit circle. And if you take any point on the unit circle, you can write, if this angle is theta, this is cosine theta plus I sine theta. And you can write theta as 2 pi t. You get every point on the unit circle. So the image of this homomorphism F is the circle of radius 1, the unit circle. So spend a couple of minutes right now and just think about this, because it's a basic problem and it's important to understand it. All right. Any questions about this, or any parts I should go over? All right, well, let's look at problem 2. So suppose we let H be the set of all points x comma x for all real numbers x. So this is just a set of points in the plane. These are all the points x, y, where y equals x. So this is H. H is just the line y equals x. Okay. And we want to prove this is a subgroup. Well, if you take x comma x and y comma y and you add them, you get x plus y comma x plus y. Again, the first coordinate equals the second coordinate. So H is closed under vector addition. Zero, zero, that's the origin. The x coordinate equals the y coordinate, so that's in H, but that's the identity. So H contains the additive identity in just 0, 0. That's the identity element for addition of vectors. And if XX is in this set, then minus x is also in the set, because again, they have the same x and y coordinates, and XX plus minus x is x minus x is 0, 0. So H contains the inverse of all of its elements. Right? If you take the element XX, the inverse is just minus x. So H is a subgroup. Again, if you wanted to describe this in terms of high school algebra, H is the set of points in the plane R2 such that y equals x. Right? That's just the line y equals x. Then we want to calculate some cosets. So H is the set of all points x comma x contained in the additive group. And compute the left coset 0, 3. 0, 3 is some point in R2. What is that left coset? So this means you add 0, 3 to every vector in H. So this is everything in the form 0, 3 plus x comma x for all x in R, because these are all the vectors in H. And when you add these up, you get x comma x plus 3. What is that? This is all the points x, y in R2 where the y coordinate is x plus 3. What is that? Well, that's just the line y equals x plus 3. This was H, 1, 2, 3. This is the line y equals x plus h. It's just the line parallel to H with y-intercept 3 and slope 1. Right? That's the left coset. So the subgroup H is this line y equals x. This particular coset is the line y equal x plus 3. It's parallel to H, but with a different y-intercept. Okay. Questions about this? Let's take,
So professor,
yeah,
so for that, it's just put it in that form, and then to prove it, we just draw the graph. There wouldn't be anything else.
well, no. Drawing the graph is the answer, and and how do you get the answer?
Oh,
This
okay.
is the argument that says that the coset 0, 3 plus h is the line y equal x plus 3.
Okay, gotcha.
So this is the proof, right? Or
Okay.
this is the calculation that tells you what the coset is, and this is just drawing a picture of the answer.
Okay.
Right? Now let's take another coset. Suppose I take 2, 5 plus h. So this is all the vectors in the plane of the form 2, 5 plus x, x. Right? I'm just adding 2, 5 to every vector in H. So that is x plus 2, x plus 5. And what is this? Well, I can write this, if I like, as x plus 2, and x plus 5 is the same as x plus 2 plus 3, because 5 is 2 plus 3. And let's say I let x prime be equal to x plus 2. Just make that substitution. So this is all points of the form x prime plus 3. And as x runs through all real numbers, x plus 2 also does. So if I make this substitution, I see that this coset is exactly the same as this coset. So if you want to know what is this coset, well, it's the set of points on this line. So this red line is equal to 0, 3 plus h, but it's also the same as 2, 5 plus h. Right? They're just two different ways to represent the same coset. Or that makes a very concrete statement of the fact that you can represent a coset in infinitely many different ways. So this set and this set, they're exactly the same set. It's this set of points. Okay. All right, well, there's one more part to this problem, which is compute and describe. Problem was to compute and describe geometrically. So here's the computation, and this is the geometrical description. And the last part of the problem is to find all all of the left cosets. So we have the additive group of vectors, R2. This is all vectors x, y, where x and y are reals, right? That's just the ordinary plane. We have the subgroup H, which is all vectors where x equals y. The second coordinate equals the first coordinate. That's just the line y equals x, that's H. And suppose we let AB be any vector in R2. We want to compute the left coset AB plus H. And see, maybe to make it easier, I'll start with, instead of an arbitrary point AB, a point on the y-axis with 0C. So first, for any real number C, I want to compute the left coset 0, C plus H. So this is all points of the form 0C plus x, x. When I add these together, I get x plus c, which is just the set of all points x, y, where y equals x plus c. Right? That's what this coset is. And this is exactly the line with slope 1 and y-intercept c. So parallel to h. So this line is the coset 0c plus h. So we certainly get so the set R2 mod h, right? This is what we mean by the set of left cosets. It certainly contains all lines with slope 1. That is, all lines parallel to the line y equal x. Because for any c, the line y equal x plus c is a coset. But what about the general case? Suppose I take AB plus H. So this is everything of the form AB plus x, x for all x in R. This is a set of everything of the form x plus A, x plus B for all x in R. And again, I can do the same sort of trick I did a moment ago. I can write this is x plus A, and x plus B is the same as x plus A plus B minus A. And if I let x prime be equal to x plus A, this is everything of the form x prime comma x plus b minus a, x prime plus b minus a. And as x runs through all the real numbers, so does x plus a. But this is exactly the coset 0 b minus a plus h. That is, if I can write this as 0 c plus h, with c equal to b minus a. So every coset is a line parallel to y equal x. And so the set of all left cosets R2 mod H is the set of all parallel lines. Right? Okay. So I'm going to pause for a minute or two, and I want you to have a chance to think about this. And if you have questions, to ask me questions. So we're just going to pause. Okay. Any questions about this? These are really basic calculations in group theory. So these are things that you have to be able to figure out. All right. Let's look at the next problem. This is problem 3. So we're looking at the cyclic group of order 18. That means this is a group with 18 elements generated by something I'll call A. So it consists of the elements E, A squared, A cubed, A to the 16th, A to the 17th, and that's it, because A to the power 18 is the identity again. And the rule for multiplication is that A to the I, and of course, A to the 0 is just the identity. A to the I times A to the J is A to the I plus J, and I should say mod 18, because if I plus J is greater than 18, then you just reduce it mod 18. So this is the cyclic group. Again, these are fundamental groups that you have to know. You have the integers and the real numbers and the complex numbers, and you have congruence classes Z mod MZ, which is an additive cyclic group, and you have the multiplicative cyclic group gamma. So what is the subgroup generated by A cubed? This means the smallest subgroup of the group that contains A cubed. And we usually put brackets around the element. This means the cyclic subgroup generated by A cubed. So it's going to be in there. It has to contain the identity, has to contain A cubed. If you multiply A cubed by itself, A cubed squared is A to the 6th. A cubed cubed is A to the 9th. A cubed to the 4th power is A to the 12th. A cubed to the 5th power is A to the 15th. A cubed to the 6th power is A to the 18th, which is just the identity again. You're back to the identity. And you can just see, suppose we took A cubed to the 7th power. That's A to the 21st power. That's A to the 18 plus 3. Because 18 plus 3 is 21. That's A to the 18th, A cubed. A to the 18th is the identity. We're just back to A cubed again. So the only elements of this set, the distinct elements of this set, are E, A cubed, A to the 6th, A to the 9th, A to the 12th, A to the 15th. That's it. So the cyclic group of order generated by A cubed has 6 elements in it: E, A cubed, A to the 6th, A to the 9th, A to the 12th, and A to the 15th. So this is the subgroup generated by a cubed. Any questions about this? All right. What about the subgroup generated by a to the sixth? Does someone want to calculate this and tell me what are the elements in this subgroup? It's just the powers of a to the sixth. So you have the identity, which a to the 0, or a to the 6 to the 0.
Yeah, a to the 6 and a to the 12.
Yes, thank you. Exactly right. A to the 6. A to the 6 squared is a to the 12th. A to the 6 cubed is a to the 18th. But a to the 18th is the identity. You're back to the identity. And then it just keeps repeating. So this subgroup only has 3 elements, e, a to the 6th, and a to the 12th. What about part C? So this is problem 3. So we have gamma 18, which is the cyclic group of order 18. And the subgroup generated by a cubed is e, a cubed, a to the 6th, a to the 9th, a to the 12th, a to the 15th. The subgroup generated by a to the 6th, so this group had 6 elements in it. The subgroup generated by a to the 6th is e, a to the 6th, a to the 12th. What about the subgroup generated by a to the 9th? So that has e, a to the 9th. But once you calculate a to the 9th squared, that's a to the 18th. That's the identity. So this subgroup only has 2 elements in it. Okay. And then the final part of this problem, let's see, 3, 6, 9, 12. That's right. Calculate the subgroup generated by a to the 12th. So let's see, what is that? So a to the 12th to the 0th power is a to the 0 is the identity. Sorry, is there a question? A to the 12th to the 1st power is a to the 12th. A to the 12th squared is a to the 24th. Of course, 24 is 18 plus 6. So that's a to the 18 times a to the 6th. But a to the 18 is the identity. This is just a to the 6th. A to the 12th to the third power is a to the 36. 36 is 18 times 2. This is a to the 18th squared, which is e squared, or e. So by the time I take a to the 12th cubed, I get back to the identity. So the subgroup generated by a to the 12th just consists of these three elements. In fact, it's exactly the same as this subgroup generated by a to the 6th. Okay, any questions about this? Let's look at problem 8. So if you have a group G and an element X in G, we say that X has order n, though this is what I'm going to define, if n is the smallest positive integer such that x to the n is the identity. And positive means at least one. 0 is not positive. And we also say x has infinite order if it doesn't have order n for any n. If x to the n is not the identity for every positive integer. So for example, in the cyclic group gamma 18, A generated by A, the element A has order 18. 18 is the smallest power of A, which is the identity. A squared has order 9, because if you take A squared and raise it to the 9th power, you get A to the 18, and no smaller power gives the identity. The element A to the 6th has order 3. The element A to the 12th also has order 3, right? That is, these are things we calculated in problem 3 a few minutes ago. In the multiplicative group of non-zero real numbers, the element 2 has infinite order, because when you start taking the powers of 2, right, these are the powers of 2, 2 to the n is never equal to 1. So this is an example of an element of infinite order in a group. And as I had remarked in class previously, if you take an element A the order of A is exactly the number of elements in the cyclic subgroup that A generates. Because you're taking powers of A and you stop when you get to the identity, and that's when you stop. So in problem 8, we have a homomorphism from the group G to G prime. This is a group homomorphism. That means, again, f of x, y is f of x times f of y for all x and y in the group. And part A is to prove the following. Prove that if an element A in G has order m, and if the element f of A, which is in G prime, has order d, then d divides m. So this is a proof. We have to prove this. So what is it that we know? We know that f of A to the d is the identity in G prime. I'll call it E prime. And d is the smallest positive integer for which this is true. So if you take the element f of A and raise it to the dth power, you get the identity in G prime, and no smaller power of G works. We also know that in the group G, A has order m, so A to the m equals the identity, which means that if I take f of E, that's the same as f of A to the m. If E equals A to the m, then f of E equals f of A to the m. But we also know that the identity gets sent to the identity under every homomorphism. So E prime is f of E. And f of A to the m is f of A to the power m. So what do we know? We know that f of A has order d, so f of A to the d is E prime, and f of A to the m is also equal to E prime. But there's a lemma I can prove in general, or I can prove it in this case, but let me just prove it in general. So this is a fact about orders. If A, or if an element x has order d, and x to the m is the identity, then d divides m. And the proof goes as follows. By long division, you can write m as d times some quotient plus a remainder, where the remainder is between 0 and d minus 1. So the identity E, which is x to the m, that's x to the dq plus r. That's x to the dq times x to the r. X to the dq, that's x to the d to the q. This is x to the d is the identity. X is order d. So this is just equal to x to the r. So E equals x to the r. But r is smaller than d. R is at most d minus 1. So r cannot be positive. So r has to equal 0, and m equals dq. That is, d divides m. So that's the proof. So for homomorphism, if A has order m, then f of A has an order which must divide m. Any questions about this? Let's look at part B of this problem. So this is 8b. So now we're told that this homomorphism from G to G prime is actually an isomorphism. So that means F is 1 to 1 and onto, as well as being a homomorphism. And we want to prove A in G has order m if and only if f of A in G prime also has order m. So we can give a proof in different ways. For example, so we can say let D be the order of f of A. So by the first part of this problem, then D divides m, because we proved in the first part of the problem that the order of f of A divides the order of A. So f of A to the D, sorry. So if A has order D, f of A to the D is the identity. If D is the order of f of A, it means f of A to the power D is the identity. But because f is a homomorphism, this is f of A to the D. But also, so f of A to the D is the identity. And f of E is the identity. So we have f of E is the identity, and f of A to the D is the identity. So that means A to the D equals E, because f is 1 to 1. if f of a to the d is the identity, that means f of a to the d is the identity, but also f of e is the identity. So if these two elements, e and a to the d, both get mapped to e prime, they have to be equal. So a to the d equals e, which means m divides d, because a has order m. So we have d divides m and m divides d. Therefore, m equals d. So in the case of an isomorphism, a and f of a have the same orders always. Any questions about this? Let's look at problem 6. So again, we have a homomorphism, F, let H be a subgroup of G. So f of H, this is everything of the form f of x, where x is in H. So it's like here we have G, G prime. Inside of G, we have the subgroup H, and it gets mapped to something over here. Right? H is a subgroup of G. F of H, which is the image of H under this homomorphism F, is a subgroup of G prime. And we want to prove F of H is a subgroup of G prime. So what does it mean to be a subgroup? It's a set of elements. It has to be closed under multiplication and contain the identity, contain the inverse of everything. So suppose we let y1 and y2 be an f of h. So that means that there have to exist x1 and x2 in H such that f of x1 equals y1 and f of x2 equals y2. So y1 times y2 is f of x1 times f of x2, but that's f of x1 times x2. And that is in f of h because h was a subgroup. And x closed under multiplication, so x1, x2 is in h. So if you take two different elements over here, their product is in there. So that's the first thing you have to prove to have a subgroup, is closed under multiplication. Second, E is in H, and so f of E, which is E prime, is in f of H. So f of H contains the identity. And if Y is in f of H, then Y equals f of x for some x in H, which means Y inverse. So that's f of x inverse. But we prove that f of x inverse is f of the inverse of x. And that is also in f of h, because h is a subgroup and x inverse is in h. So that's the end of the proof. If you have a homomorphism f from G to G prime, and you take a subgroup H of G, and you look at its image f of H and G prime, we want to prove f of H is a subgroup of G prime. So we show first is closed, f of H is closed under multiplication. It contains the identity, and it contains the inverse of each of its elements. And the second part of the problem is to show if you go backwards from G prime to G, a subgroup goes to a subgroup also when you go backwards. Of course, we have to explain what going backwards means. So in general, if you have any function from G to G prime, these can just be sets if you like. And if you take any subset, let's draw a picture. Here's G, here's G prime, here's the function f. Here's some H prime. You can let f inverse of H prime be every element x in G, such that f of x ends up in H prime. And it doesn't end up over here somewhere. So you have all the elements in G that f sends into H prime. And that's what is called f inverse of H prime. And we want to prove that if H prime is a subgroup of G prime, then f inverse of H prime is a subgroup of G. So again, we have to prove the three requirements for a subgroup: that is closed under multiplication, contains the identity, and contains the inverse of each of its elements. So let's do the first. Show f inverse of H prime is closed under multiplication, so that x1 and x2 be f inverse of H prime. So if x1 is in f inverse of H prime, that means f of x1 is in H prime, and f of x2 is in H prime. And H prime is a subgroup, so it's closed under multiplication. So f of x1 times f of x2 is in H prime. But because f is a homomorphism, f of x1 times f of x2 is f of x1, x2. So f applied to the element x1, x2 sends you into h prime, which means x1, x2 is in f inverse of h prime. So this inverse set is closed under multiplication. If x1 and x2 are in f inverse of h prime, so is the product. Show the identity is in f inverse of h prime. But this is easy because f of e is always the identity is in h prime. So f of e is in h prime, so e is in f inverse of h prime. And we want to show that x in f inverse of h prime implies x inverse is also in f inverse of h prime. Well, if x is in f inverse of h prime, that means f of x is in h prime. That's the definition. But this is a subgroup. So f of x inverse is in h prime. But the inverse of f of x is f of x inverse. So f of x inverse is in h prime. So x inverse is in f inverse of h prime. Any questions about any of these so far? This is all important results and techniques in the beginning of group theory. Any more questions? Any questions? Well, this is all really good stuff, so let's just keep going. Any questions from either of the previous homework, 7 or 8, that you would like me to do? right, well, let's see. So this is still homework 9. Let's look at problem 12. So we have a group G, an element A in the group, and you define a function, I'll call it C sub A, from G to G. So we define by C sub A of X is AX A inverse. And this function is called conjugation by A. Maybe let me start by showing that C sub A is a homomorphism. So C sub A of XY is AXY A inverse. I can write this as AXY A inverse and put in the identity there. That certainly doesn't change anything. That's certainly true. But of course, the identity is A inverse times A for any A. This is AX A inverse A, Y A inverse. And if I think of it like this is C sub A of X, and this is C sub A of Y. So that proves that this function is a homomorphism. What about composition of functions? So for elements A and B in the group, I can look at the function C sub A and the function C sub B and compose them. So what is this equal to? Well, you learned about composition of functions in pre-calculus. The chain rule tells you how to differentiate the composition of two functions. So CA CB of X, this means CA applied to C sub B of X. That's the definition of composition of functions. This is C sub A, and what is this element? This is BX B inverse. And what is C sub A of that element? That's A BX B inverse A inverse. That's ABX B inverse A inverse. But of course, you know that the inverse of AB is B inverse A inverse. So this is AB times X times AB inverse, and this is exactly C sub AB of X. So therefore, CACB is CAB. So we have this nice rule for composing conjugations. If you compose conjugation with A and conjugation with B, you get conjugation by AB. And this function C sub A is not only a homomorphism, it's an isomorphism. So let's prove C sub A is an isomorphism. So how do you prove that C sub A is one? We know it's a homomorphism. You have to show it's 1-to-1 and onto. So why is it 1-to-1? So that X, B, and G, and we want to find Y such that C sub A of Y is equal to, sorry, let's prove that it's onto. I guess that's what I started to prove. So that X, B, and G, or let's say, yeah, that X, B, and G we want to find a y such that C sub A of y is equal to x. That's the same as saying AY A inverse is equal to x. But this is a group equation that you can solve for y. If you multiply by A inverse on the left and by A on the right, here we get E, Y, E. This is just y. So y is A inverse x A inverse. So C sub A of A inverse x A inverse x A is equal to x for all x and g. So therefore g is on, therefore the function C sub A is onto. And then we have to show that C sub A is 1-to-1. So if C sub A of x equals C sub A of y, that means AX A inverse equals AY A inverse. So if you take AX A inverse, which is equal to AY A inverse, and you multiply on the left by A inverse, that's still equality. And you multiply on the right by A, that's still equality. But these are the identity. So X equals Y. And that's the end of the proof. Any questions about any of these? Okay, so study hard and work problems. The whole exam is on group theory. So there are 3 homework sets, which are like the review sheet, if you wish, you know, plus everything that we've done in the lectures, of course. But I'll be back on Friday morning for a review session. It's completely voluntary, but the best thing is if you can have questions in advance to ask, and we'll go over them. Okay. If not, then we're done for the day. Bye, everyone.